In this lectorial, we're going to consider the concept of maximum sustainable yield and how it can be used or has historically been used in single stock assessment of fisheries. So the concept of maximum sustainable yield revolves around ascertaining that population size of a particular species at which its rate of growth is population growth is maximal. And what we are seeking to do is maintain the population at that size so that we can extract individuals at the greatest rate while still maintaining the sustainable population. So what we're hoping to do is offset with our fishing mortality exactly the number of new recruits that are turning up in the environment. And so the goal is to enable the population to continue to be productive indefinitely so we can continue to fish it. To understand the concept of maximum sustainable yield, we need to understand the logistic population growth. And this is a concept that those of you who have done MAR202 will be very familiar with. This is what the logistic growth curve looks like here. And so on the x-axis, we have number of generations, well, that could also be time. And on the y-axis, we have the size of a population. And so just imagine that a species of fish turns up in a new environment for the first time, and that environment is suitable for the fish. What is going to happen initially is that, provided that there is someone for that fish to mate with, initially the rate of population growth is going to be very, very rapid because resources are unlimited. So we might initially have 2 fish, those fish mate, then we end up with 4 fish, those fish mate, then we might end up with 8 fish, and so we might have this very, very rapid rate of growth. But what is going to happen through time as our population really starts to grow is that resources are going to start to become limiting. And as resources start to become limiting, mortality is going to go up. And so our population growth rate is going to slow. And eventually we'll reach the carrying capacity, which is the maximum number of individuals a particular environment can sustain. So with maximum sustainable yield, what we're looking to do is to identify that point in a population's growth at which the rate of growth is the greatest, because at that point we are able to extract the most number of fish to offset but not exceed the rate at which new individuals are entering the population. And so if we look at this curve here, basically what we're looking for is the point on this curve at which the slope is the steepest, because the slope of this curve is actually representative of population growth rate, change in population size over change in time. And so you will notice that the steepest point is actually here. So this is the maximum sustainable yield. And that population size is exactly halfway between the carrying capacity and 0. Okay, so pretty simple. Our maximum sustainable yield is half of the carrying capacity of a particular environment. So that seems really simple in theory, but in practice it's much more tricky. Because first of all, it's actually quite hard to produce a population growth curve for a particular species. We need to know how many species are in the population, the number of offspring they produce at certain times in their life history, and obtaining reliable data can be quite difficult, and so as a consequence it can be quite difficult to estimate maximum sustainable yield. The second problem is that even if we are able to reliably identify that point, that population size at which the population is growing at the greatest rate, and theoretically what the maximum sustainable yield is going to be, we can't always guarantee that although we set quotas at this level, they are going to be adhered to. So we may well have issues with illegal fishing. Non-compliance can be a big issue. The third issue is that carrying capacity is not actually static and unchanging. Carrying capacity can actually vary considerably with the environment. And because the maximum sustainable yield is half the carrying capacity, the maximum sustainable yield is also likely to change through time as well. And so just for example, this slide here is basically showing the differentiated curve from the previous graph. So what we've got here is population size on the x-axis, and we have got recruitment or arrival of new individuals into the population on the y-axis. Okay, and so here is 0, and these endpoints here represent the carrying capacity. And at half the carrying capacity here, we're going to have the greatest rate of population growth of new individuals coming into our population. So that's the maximum sustainable yield. So just imagine that we set our maximum sustainable yield under conditions at which our carrying capacity is over here. Okay, so we're extracting this number of individuals. Just say the environment changes and is no longer able to sustain as many individuals. We are now going to be extracting fish at a much larger, a greater rate than this environment can actually sustain. So what are those factors that actually affect carrying capacity? Well, there can be density-independent factors. So there can be disturbances such as storms. If we're talking about a terrestrial environment, there could be drought that actually wipe out individuals in a population and in a way that is independent of how many individuals there are in that population. Pollutants also can affect the carrying capacity. So things like DDT poisoning, the action of pollutants in reducing population size is independent of that population's density. We also have density-dependent factors, so the availability of food. So you could imagine that through time, food resources may vary depending on whether it's been a good year for productivity or a bad year for productivity. And that is in turn going to influence how much food is available, how much resource there is available for each individual. And beyond a certain point, or below a certain point, there is going to be insufficient food per individual for that population to be sustained, and so individuals are going to die. Things like competition for space can also influence carrying capacity, and density-dependent diseases as well. The other issue with maximum sustainable yield is that it also has quite a few assumptions that are not necessarily true in the real world. So first of all, maximum sustainable yield assumes that all individuals are identical. So they're all the same size, they all consume the same amount of resource. It assumes that there is no immigration or emigration to our population. So the only change in population size is a result of births and deaths. But in many instances, this is not the case. There can be individuals that are migrating in from other areas or migrating out. And the concept of maximum sustainable yield is very much based around single stock assessment. So it really assumes that species of fish actually exist in isolation and do not interact. However, often what we see is not just a single species of fish consuming a resource, but actually multiple species of fish consuming that same resource. And so even though the availability of resource might be sufficient to sustain 20 individuals of a particular species, by only considering a single species at a time, we're not taking into consideration that there might actually be 20 individuals of another species that are also consuming that resource. And so actually we don't have enough resource to go around. So what is the history of maximum sustainable yield? Well, it's actually quite an old concept. It was developed in the 1930s in New Jersey, and it was initially adopted by the International Whaling Commission, the Northwestern Atlantic Fisheries Organization, and by several countries. By 1955, the US had actually manoeuvred to have maximum sustainable yield declared the goal of international fisheries management. So in other words, by this point in time, it was a pretty widely accepted and recognised method of management. By the 1970s, though, people were starting to question whether maximum sustainable yield was really adequate to deal with real-world complexities. Because of some of the issues that we've just talked about. But nevertheless, in 1982, maximum sustainable yield was actually incorporated into the United Nations Convention for the Law of the Sea. But by 1990, what we were starting to see was the collapse of fisheries that had been managed according to the principles of maximum sustainable yield. So here is one example. This is the Peruvian anchovy fishery, and this is landings in millions of tons. Okay, so you can see through time, initially what happened is that the fishing harvest increased, perhaps because the population size was great, but then we had this crash and collapse of the fishery in the 1970s because the rate of harvest exceeded the rate at which this population could actually sustain. Subsequently, with reductions in fishing, we've had some recovery. But this is a demonstration how fixed quota harvesting can go horribly wrong. So the question I'd like to leave you with is there a better way to manage fisheries? And so in the remainder of this module, we're going to consider some different ways of managing fisheries that not only consider fish in isolation of one another, but take a more ecosystem-based approach to management.